This is going to be the derpiest video we've ever made. Okay, welcome to Calbeckistan, a place where everybody can learn math. And today, we're in my house. My lovely and very pregnant assistant, who is also my wife, filming today. Today we're going to be talking about graphing exponential functions. So hopefully by the end of today, you'll know how to do that. Alright, so we're going to graph exponential functions. You have to understand the basic format of exponential functions. So with it linear, we're kind of used to seeing it. We've seen y equals mx plus b. Okay, you guys have seen that a million times, and you kind of understand that the different pieces have different, the different parts of the equation have different roles. So the m represents the slope, the b represents the y-intercept, and the x and the y can change because they're coordinates, and so those are the things that are always changing. So we're going to look at the same kind of template for our exponential functions, and it looks like this. A times b to the x power. Now if you're in a higher level math, you might see plus c on the end there. We're not going to be talking about that today. Each of these has a different role. So when we're looking at this, the a is what I like to call the starting value. And I use that intentionally. Some people will call this the y-intercept.
It looks like valve.
It looks like value. My writing's just fine. Okay? That's totally value.
Now that you put that little the tail and the U.
It was there the whole time. So this is starting value, but it's also, you can think about that if it's helpful. This is going to be the y-intercept. Okay? Starting value will help you more when we're talking about word problems in the next video. This I like to call the multiplier. Okay, and I call it the multiplier because exponents, they multiply things again and again and again. So this is the thing that's getting multiplied again and again. Now I can tell you all of this, but really it's easier to see an example, and this will make more sense as we go. So let's take a look at this right here. Look at this equation. Y equals 3 times 2 to the x power. And what I find really helpful sometimes is to make a table, and then we can kind of see what's going on with the function. And when you're making a table, using x and y, always include negatives and 0. If you don't include those, you're not going to get a full picture of what the function looks like. So we'll go down to -2 maybe. 1, 0, 1, 2, and 3. And then we should be able to get a pretty good idea of what's going on here. So when we're looking at this here, let's start with 0. That's always a good place to begin on a function. So let's think about what this means. I'm going to plug in for x. I'm going to plug 0 into this equation for x. So I'm going to say y equals 3 times 2 to the 0 power. Okay, now we have to remember from our last video what we did for 0 powers. It's not 0. Okay? Anything to the 0 power is 1. And remember from PEMDAS, we start with exponents before multiplication, so we're going to do this first, which gives me a 1. So 3 times 1. So I'm going to write a 3 here, because that's the y value. And we're going to do that for all of these. For 1, we can do the same thing. We can say y equals 3 times 2 to the first power. 2 times 1 is 2, times 3 is 6. 2, I would do the same thing. I'm just going to replace this with a 2. 2 squared is 4, times 3 is 12. And 3 here. This is a little tougher. Don't let your brain juke you out here. 2 to the third power is 8, because that's 2 times 2 times 2. So 8 times 3 is 24. Now we can already start seeing there's some patterns here. This pattern is not linear. Okay, with linear functions like we have up here, you're always adding or subtracting the same number each time. But with an exponential function, what you're looking for is something that's being multiplied each time. So I want you to be looking for that, and we can see that in the table emerge right here. We can see 3 times 2 gives you 6. 6 times 2 gives you 12. 12 times 2 gives you 24. And you could continue that pattern. And this really makes sense if we look at our exponential function to begin with, because we have 2 to the x power. We're going to be multiplying 2 again and again and again, however big x happens to be. So now we got to think about negative exponents, which are always a little trickier, but you can actually cheat a little bit and use your pattern if you get stuck. But for right now, let's go ahead and see what negatives will do to my exponent. 2 to the negative 1 power. And again, remember from our previous videos, we talked about negative exponents. Negatives are opposites of regular numbers. So if my exponents normally multiply something again and again and again, negative exponents need to do the opposite of that. They need to divide again and again. So what I've got here is a division problem. That 2 to the negative 1 is the same as 1/2. So I have 3 times 1/2, and I hope you remember how to multiply fractions. Put it over 1, and you multiply straight across. 3 times 1 is 3, 2 times 1 is 2, with 3/2. And we would see that as well. If I wanted to go backwards in my pattern, I'd probably be dividing by 2 to go up on this pattern, which makes sense. Again, we could probably do this again if you wanted to. Again, we can look at the equation, or you can simply follow the pattern. 3 over 2 divided by 2 would be 3 over 4. I'll show you real quickly how we would get that. Remember, it's 3 times 2 to the negative 2 power, which is the same as 1 over 2 to the second power, or 1 over 4. So I have 3 over 1 times 1 over 4, that's 3 over 4. Okay, so we've got ourselves a nice little table here, and again, I want you to be looking for that pattern. There's a reason I call this the multiplier, because this is what's going to show up as your pattern every time. You can be able to see that in your table as you multiply. It's always going to be multiplying by whatever this number is. If this is a 3, you're going to see it multiply by 3 each time. Alright, so let's see what this looks like if we plot these points and see if we can find some shortcuts so we don't have to make a table every stinking time. Alright, so I'm going to get out my ruler here. This video is most definitely not sponsored by Walmart. Though Walmart, if you do want to sponsor me, I totally will take your money. So please, by all means, feel free to sponsor me. No, cover that up. They're not sponsored.
Oops.
Okay, yeah. Alright, so I'm just going to make a table here. Gosh. Yay, I made a table. That's awesome. Okay, should label your axes, the X and Y. And I'm just going to let each point on here be 1, so I don't have to label anything. Alright, bye Walmart. Oh, sorry. So let's go ahead and plot these. Again, I like to start at the 0. So when X is 0, that's always going to be your Y-intercept. So I'm going to have a point right here.
1, 2, 3.
Alright, we're going to try that again. This is your point right here. Thanks for catching my error.
1, 2, 3.
There we go, we got it. Alright, then we're going to go 1, 6. So I'm going to go over 1 and up 6. Maybe you can help me count this one this time. Again, my lovely, very pregnant, and talented wife, Christy. Okay, we can do 2 and 12. It's going to get pretty high pretty quick. Let's see, 1, 2, 3, 4, 5, 6. I think that's 12. And I'm not going to be able to fit 24 on here, so I'm not going to graph that. That's right, exactly. Okay, it's going to go off the table. And if you, on your graphs, don't have enough room, that's fine. Just graph whatever you have. Don't feel like you have to change your scale a whole bunch. Okay, we look at negative 1 here. That's 3 over 2. If you want to put that in your calculator, it's a little easier to graph. That's 1.5. I'm going to go to negative 1 on the X, positive 1.5 here. Again, please pardon my really bad extra dot. Negative 2 is going to be 3 over 4. That's 0.75. And I'm cutting these in half each time. So you can actually look at the distance. If I were to go back one more, I would cut it in half again, so it would be probably about there. Again, half this height. And I would do it again, it's here, and do it again, it's here. And pretty soon it just looks like it's right on top of this line. And so we can connect these dots here. That's beautiful. That's a really good exponential graph. Don't judge me. Okay. Here's your question then. If you're going to be like this, you get to be in my video. All right. Is this ever going to cross the x-axis here?
No.
Why do you think not?
I just remember it. I don't know why.
Well, let's look at the pattern. What do you think? What about the pattern
It'll
tells
never
you?
hit 0.
Why not?
I don't know the answer.
Okay.
But I know that it won't.
You're right. It won't. And the reason is I'm dividing by 2. Okay. The only way you can get to 0 is by adding, subtracting, or multiplying by 0. I can't ever get to 0 by dividing by 2. You can always cut something in more pieces. I can take this number as however small it is, and I can always make it smaller by cutting it in half. And so I'm only dividing. And what you end up here is this thing in math called an asymptote, which is really fun. Don't call your little brothers and sisters though. But what it is it's a line that your graph will never ever touch. And in our graphs, you will always have an asymptote on the x-axis. If you are in Algebra 2 or higher, you might see a plus C here. That C is where your asymptote is. You can move it up and down with this. But this is the basic shape of a function. And again, I want you to take a look at this. It crosses the y-axis at 3. That's the starting value, or y-intercept. And every point after that multiplies. Start at 3, it goes to 6. 6 multiplies by 2, it goes to 12. 12 multiplies by 2 and goes to 24, which we couldn't see. So these are the things I want you to be looking for. A couple other ways that we can do exponential graphs. So with our y equals a times b to the x power, the b always needs to be greater than 0. So b is always greater than 0, but it can be less than 1, which does some interesting things. If b is bigger than 1, it will go up, and it will look like our graph did before, like this one over here. It'll have that same shape where it's gradually going up faster and faster and faster. Okay? If b is less than 1, but bigger than 0, we have something actually pretty interesting happen. Okay, I'm just going to go ahead and draw this with my non-sponsored video. You know, teachers could always use arrays, Walmart. You could sponsor this. It'd be pretty dope. All right.
Do people say dope?
They do. Only the cool people do, though.
Oh, wow.
It's actually my goal to make students cringe every time I say stuff like that.
Oh, and your wife.
It's a fringe benefit. Okay, so here's my new graph. I'm going to give you a new function, and we'll call this one y equals 8. I'm going to put this in parentheses, but it still means multiplication, times 1/2 to the x power. All right, and so we can remember from last time that this is going to be my y-intercept. So maybe you can help me with this. 1, 2, 3, 4, 5, 6. Okay, got it that time.
Sure.
Yeah, no, actually not. I'm not going to doubt myself though. All right, now let's see what happens if we make a table. Same as last time. We've got -2, -1, 0, 1, and 2. We're going to go ahead and see what happens. If I plug 0 in, well, anything to the 0 power is, do you remember?
1.
Good job, yeah. So I have 8 times 1/2 to the 0 power, which is just 1. So this is 8, which we already plotted.
Oh, you already plotted it.
I
Look
did,
at that.
sorry. But what happens if I take 1/2 to the first power? Well, it's just 1/2.
Yeah.
So what's 8 times 1/2?
4.
It's 4. Nice job. You're starting to pick this up. So, unlike last time, I see my numbers actually going down. Do you have a prediction on what you think is going to happen here?
I think it's going to be 2.
Let's see. So 8 is times 1/2 squared. Remember, squared means I'm multiplying something by itself. So that's going to be 8 times 1/2 times 1/2. Remember, we multiply straight across. Or 8 times 1/4. 8/4 is 2. You got it right. Nice job.
Man.
You're picking this up quickly. So based on the pattern, what's happening this time? What's next?
Just gonna, oh. 1?
Yeah.
Is that right? Okay.
That's right. Yeah, it's the pattern here. I'm actually dividing by 2. But again, everything's multiplied in an exponential. So I want you to say it's multiplied by 1/2.
Oh.
Okay? Multiplying by 1/2 each time. It's cutting it in half. Which means if I go backwards, what do you think happens there?
They're gonna go up?
They're going to go up. This is going to be 16. It's doubled. Because it has to multiply by 1/2 to get 8. And this would be perfect.
32.
Good job.
I was getting there.
Oh, good. All right, so we got there.
Look at this belly. It takes a lot of my
Okay.
blood away.
This is going to be the derpiest video we ever made. Okay, we can go ahead and plot this. And what you end up seeing is it gets cut in half. It gets cut in half. And half. If we were to keep going, you see the asymptote is still there. Okay? This mother function has a nice asymptote.
Oh my.
Okay, and if we go on the other side, it would be up at 16. So 2, 4, 5, 6, 7, 8 would be up here. And we don't have room to do 32. Okay, so it's exactly a flipped version of what we had before. So what happens is when b is less than 1, your function goes down. When b is greater than 1, it increases.
Oh.
Okay, so those are the 2 ways that you're likely to see your exponential functions. There are other ways that you can change them, but for right now, I think this is a good start for you. Remember that exponential functions are always multiplying something, so if you look for that pattern of multiplication, it could be multiplied by less than 1, which means it's going to go down. This number here is always going to be your starting value or y-intercept. And anyway, I'd like to personally thank my lovely and talented and very pregnant wife, Christy. Thank you for helping me out and making this incredibly derpy video.
Anytime.
Yeah. So give me a like or thumbs up if you thought Christy did a great job today. And leave a comment. I think you're having way too much fun with this. I think we better cut it. Next time we're going to talk about applications of exponential functions and see how we can use exponential functions to model real life situations. All right, it's Calbeck. I'll see you.